All right, g'day MEC2403 3601 students. I'm just going to provide a little bit of feedback on your first quiz. I'm sorry this is coming so late, a combination of kind of the late marking and the spec cons, and then the Easter break hitting when it did meant that this is coming out only now. But mercifully, the stuff we're going to be talking about here isn't super duper relevant to what you're doing in quiz 2. Maybe some of the stylistic things, but the content in quiz 1 and quiz 2 are largely orthogonal. So take everything you hear here with a grain of salt. Maybe focus more on your quiz 2 efforts. But if you're wondering how you might be able to improve for the final exam, stay tuned. All right, let's work our way through. What I've done this morning is constructed my own solution to the quiz, kind of separate to what I've done before. And I thought we'd go through and mark this and just note the things that I might have been able to do better, or the things that I've done really well, according to the marking rubric, which we've already shared with you guys. And I'll just note again that quality assurance for your grading is available. We have 2 sessions booked this week. Feel free to come along and just check that we haven't made any mistakes. We try not to, we double check things, but we are human, and occasionally with 500 students, something slips through. All right, let's work our way through. So the first problem was to draw a free body diagram of link BED in the quiz. And to indicate on that free body diagram all of the kind of features that you would expect based on what we've done in the practicals and in the workshops, and in particular in the practice quiz workshop that we did back in week 4. And so looking at the rubric, you get a pretty good indication of the kinds of qualities that your free body diagram should demonstrate. For instance, a free body diagram should isolate only kind of one element or one body, in this case the body being link. Oh, let me draw that with a highlighter. The free body diagram isolating kind of link BED, this middle one here. And what did I need to do to achieve full marks in this question? Well, my free body diagram had to be kind of neat and tidy. Fine, fair enough. Doesn't need to be the Mona Lisa or a work of art. The one that I've drawn here is totally fine, as long as it's clear that we're talking about that link. You didn't need to have the pinholes the way that I've drawn them. A rounded rectangle would have been sufficient. I needed to only capture that link as asked, so if I had the other links attached, I wouldn't have been able to achieve full marks. And what did I need to do? I need to make sure that I indicated all of the relevant forces. That is force FAB, this one here, force FEF, this guy here, force FCD or DC, this guy here, and P, the external load. So if you had all of those loads there and your diagram was neat and tidy and your diagram isolated that link, then you met criteria 1. Okay, moving right along, and just noting, of course, as we already said, that these criteria are binary. You either needed to wholly meet them or you didn't. We didn't award partial marks within a criteria, but obviously partial marks for a question and for the quiz were available by meeting some of the criteria and not others. This can be a little bit controversial. I know that there are some students that believe that we should be partial marking everything, but the simple truth of the matter is that you can follow that rabbit hole all the way down to the center of the earth, and you need to draw a line somewhere. In this quiz, we managed to achieve, I think, a discrimination of something like 2% or 4%, which is really, really good for an in-semester assessment. So we're pretty comfortable with where we drew the line on that one. All right, working our way down, the next criteria was to make sure that you define a right-hand rule compliant labeled Cartesian coordinate system with your free body diagram. So that's this guy over here. It's right-hand rule compliant because if you curl your fingers kind of from the X direction to the Y direction, your thumb points out of the page. And so if you had drawn, let me draw a poor free body diagram. If I had drawn it like this with X and Y like that, that would not have been right-hand rule compliant. The right-hand rule compliantness of your free body diagram is not going to be a determining factor in whether you can get the right answer in this question, but it will be a determining factor in whether you get the right answer in so many more of your questions all the way through your degree. And so we're building that skill set in you nice and early. Right-hand rule compliance is extremely important, and it's something that you should carry through in all of your solid mechanics problems, in all of your dynamics problems, and if you're going into mechatronics or robotics, in those problems as well. Okay, cool. So needed a right-hand rule compliant labeled free body diagram. So needed to make sure I have an X label and a Y label on there. It was not sufficient to simply draw the coordinate system on there and not label them. The reason being that later, when you construct your equilibrium equations and you say that you're taking the sum of forces about X or Y, without these labels, those claims don't mean anything. If you don't tell me what X and Y are, then you can't say you're taking a sum of forces about X or Y, or a sum of moments about Z or a particular point. And the labels are essential for you to be able to do that. Okay, I'm just going to rub those out. I needed to make sure my linkage forces assume the directions correct with what the question asked. So the question asked for you to assume that links A, B, and C, D were in tension, and that link E, F was in compression. And there's kind of a mark associated with each of those assumptions being correctly represented on your free body diagram. So if A, B, and C, D are to be in tension, then they're going to be pulling on this associated link. They're going to be pulling on link B, E, D. So you should expect A, B, and C, D to be pointing downward. And if EF, because it's on top, is to be in compression, then it's going to be pushing on link BED. And so that one too should have been pointing down. Potentially a little bit tricky that they all ended up pointing the same way, even though some are compression and some are tension, but some were on top and some were on the bottom. So it kind of all makes sense. And the direction of P kind of comes into its presence here, but interestingly, we didn't assign a mark for you drawing P on the right way. So keep that one in mind too. All right, so all in all, you could have taken home 1/6 of the problem marks by simply following the guidelines that we kind of set out for you in every practical problem that we've worked through, and in particular in the practice workshop and the practice exam that we did together. That is by drawing your free body diagrams neat and tidy with all of the relevant forces, with a right-hand rule coordinate system, and making sure that the directions of your forces on the diagram align with whatever assumption you're making about something being in tension or compression. Okay, amazing. Let's move on to problem 2, where we were asked to construct the sum of forces equation and the sum of moments equation relevant to our free body diagram for this problem in order to demonstrate these two kind of identities, that the net force kind of looks like this, and that the forces in the links A, B, and C, D are equal. And so if we take a look at the criteria, you'll see that we were far more interested in your method here than we were about your numbers. This is going to be true of everything that we do in this unit. We don't really care at all about your numbers. In the real world, you're going to be using Excel and calculators to determine those things. We care far more about the method that you use to calculate them. Looking kind of from left to right, the first criteria was that you needed to write a verbose equilibrium equation argument for force in the vertical direction. So depending on how you defined your coordinate system, vertical could have been X or Y, though I think most people would have defined Y to be vertical. That begins with sum of forces equals 0 and ends with the expression shown. Here is an example of an argument that satisfies that criterion. It's verbose because I've written out these things kind of line by line by line. We talked about in the practice exam workshop kind of spreading your argument out over a number of lines and adjoining those arguments with good mathematical language like and or implies or therefore. And so that's what we were looking for here, that you begin your argument with sum of forces in the y direction equals 0, that you follow that through with some sort of implies symbol, and that you end that argument with the expression that we asked you to show. In this case, that the external load being applied to this body P is equal to the forces kind of as shown. And so if you did that, regardless of whether you managed to get some of the intricate details correct, if you laid out your argument in a kind of mathematically sound way, and it was verbose, you met that criterion. And you were also asked to do the same thing for moments, to write a verbose moment equation argument beginning with sum of moments equals 0 and ending with FAB equals FCD. It was not sufficient for you to simply say that this system demonstrates symmetry and thus those loads must be the same. Anything that you can claim occurs because of symmetry, you can prove with a sum of moments argument, and we'd like to see you do that. Importantly, as you were writing out this argument, we did want to see these definitions, sum of moments about a point, sum of forces in a direction, and we really, really wanted to see, though we didn't mark you down, what direction you're indicating as positive. I strongly recommend that you do this in your future quizzes and future endeavors, include this kind of direction indicator here for your sum of moments. It will help you avoid confusion and it will help your marker know what you're trying to say. If you don't put that indicator on there, then we're going to assume that positive moments are those with respect to a positive theta in your coordinate system. In other words, curling from X to Y, kind of going this way, right? And so you are allowed to take moments with whatever direction you like is positive. But if you'd like to disagree with your coordinate system, you must clearly indicate it on this sum of moments claim here. And so the same deal should have had a nice logical argument that kind of follows, steps these things line by line by line, and ends with the given expression. Okay, these other two criteria, I needed to make sure that the signs of my forces and moments agree with the coordinate system in my free body diagram. So looking over here on the left, when I've taken my sum of forces equation, the net force being equal to 0, you'll note that P is positive, and it's positive because my coordinate system defines, let me just delete this, defines Y as being positive. So anything which points up is positive. And you'll note that everything else on here, so FAB, FCD, and FEF are negative. And that's because my coordinate system defines Y as positive upwards. So those things which are pointing downwards are negative with respect to that coordinate system. And the same goes for my moments, depending on what direction I've taken as positive and where my point of interest is for taking moments, I might have positive signs or negative signs. So because I took the middle point and because I've defined the counterclockwise direction as positive, I've got a positive sign on this guy and I've got a negative sign on those guy. As long as it agrees with your assumptions and your coordinate system, and failing a definition here, what you've written on the coordinate system, then you're okay and you would have received full marks for that. Finally, to receive full marks, you did need to provide clear, neat, and logical mathematical working, and your arguments should have followed each other. We didn't penalize you for not using the apply symbol, especially since many of you spoke to me about how good mathematical language was not something that was taught explicitly in your prior units. That's okay. We're teaching it explicitly to you now. We will be expecting this in your future arguments, but it was sufficient for you to have laid these things out in a way that was easy for us to follow. And even if you wrote things out in English, long form English, that would have been okay as well. But we were looking for like these kind of bridging arguments. This thing is true and this thing is true. We were looking for like neat ordering of things, either by one way you might make things neat is by aligning all of the equal signs so that things line up. Another way that you can make sure they're neat and orderly is by using the implies and therefore symbols. Good mathematical arguments should be easy to read and you should be able to read them out in English. So if you had that present in your thing, if it was easy to follow, if the working was clear and orderly, you would have received full marks for that criterion. Okay, working our way down now. This one's quite a long problem, so I'll just quickly jump down to the relevant criteria. The first criteria was that you needed to compose a delta equals FL and EA, a Flee equation, for every link, noting the correct FL and E and A in every case. So it would have been totally fine and sufficient for you to have defined them this way with FL and EA being pronumerals. And in fact, I would recommend that you do that in all of your working. There is no need for you to make your life hard and substitute things in right at the start of your problem and then carry these kind of cooked numbers all the way through your working. It's totally fine for you to leave these things as pronumeral and then wait to see what cancels and substitute in the remainder at the end. So if you had written this and you clearly had the right subscripts on all of your deltas, that would have been totally fine. We would have been okay with that. Okay. You also needed to explain that due to symmetry and or common material properties and linkage forces, delta AB and delta CD are the same. So in this particular instance, a symmetry argument would have been okay because it's a compatibility argument rather than a kind of kinetics argument. When you're describing the kinematics of the system or you're talking about the way that things move, drawing a picture or making a convincing English language argument would be sufficient. In my case here in this solution, what have I done? I've said that because these things have the same linkage force, we've previously shown that, we did that rigorously through a moment's argument, and because these links have the same length, E and A, then mathematically I can say that delta AB and CD are the same thing. They're actually exactly equal to each other because all of their constituent components, F, L, E, A, are equal. So if you wanted to kind of go to this level of rigor in making that claim, you could have. If you wanted to explain due to symmetry for a compatibility kind of kinematics motion type argument, that would have been okay as well. The third criterion was explaining that because link BED is rigid, any delta seen by the link EF must have been the same as the deltas seen by AB and DC. And so for my argument here, I made a pretty nice, I hope, English language argument. I said further, because link BED is rigid, any amount that EF compresses, that top link compresses, A, B, and CD must stretch. And this is a consequence of that thing being in the center and those links being on the outside and those links being subject to equal deformations. So any amount that the top one shrinks, the other two must equally stretch. They're not stretching in a way that they add, like some of the other problems we did in the practicals. They're stretching in a way that they are equal. They're both seeing the same deformation as the link above. So that would have been fine. If you made an argument kind of like this, you were all good. If you drew a picture, you were even better. But of course, this is a binary criteria, so even better is just for your own satisfaction. Finally, we were required to rearrange and equate the force in the link to prove the given expression. And so it would have been nice to see, again, a nice, well laid out mathematical argument here. So I wrote mine in English language. I said setting these two things equal. I set them equal. I rearranged for the thing that I was looking for. And importantly, I worked with pronumerals until the end and then substituted in my values, but you could have done the same thing. And doing so gives you the expression that you asked for. These numbers were different, obviously, in the different test versions, but in the one that I was looking at, I think this is the Thursday version, it was 0.222. All right, moving on to problem 4. I have constructed a number of equations here, but again, let's jump down and look at the criteria that you were marked against. So the first criteria was that you should have used a substitution or row reduction or elimination to solve for the set of simultaneous equations. I don't mind how you solve your simultaneous equations. Math is a tool that you're using in this unit, and so whatever your preferred method of solving is, I'm encouraging you to do that. I will alternate between these depending on whether a problem is like strictly linear. I might use a row reduction. I really like working in matrix form. Occasionally I'll jump over and use a direct substitution or elimination, or otherwise make a good argument for why an equation should be solved that way. So I'm happy for you to use whatever you like, and all were considered valid for the sake of solving this problem. And so you can see in my argument here, the first thing I've done is I've pulled out the relevant equations that we're going to be working with to make this solution. I've identified that there are 3 of them, which is good because there are also 3 unknowns amongst these equations, FAB, FEF, FCD. So 3 equations in 3 unknowns, something that we can solve. And then I've made this substitution argument, it looks like, to solve. So I'm performing substitution 3 into 2, and then 1 into 4, and then 5 into 1 and 3 to arrive at the value that I was asked to get. So that's fine. I use substitution or elimination to solve the set of equations. Uses good mathematical language to explain what you're doing at every step, e.g. by labeling equations or writing sentences such as sub 2 into 1 or using the imply symbol. So I've done all of those here. The imply symbol makes an appearance in many cases. I have these kind of vertical stacking of my equivalences when I want to make an argument that follows, or a substitution or a rearrangement of what I'm seeing. I'm using this kind of mathematical language to clearly explain what I'm doing at each step. So I'm subbing equation 5 into equations 1 and 3. I'm labeling my equations as I go. Every time I generate a new one that's important that I might want to substitute later. I'm putting boxes around these things so they're nice and clear. There's no hard and fast like one rule as to what constitutes a good mathematical argument, but these are all good indicators of one. And so if you had a good number of these, you were probably okay. All right, cool. I needed to correctly calculate FAB or FCD, so depending on what you were asked to find. In that particular instance there, because we gave you the number, I think we said prove that those, or show that those forces are whatever value, 4.615 kilonewtons in this particular test. I think because we did that, when we say correctly calculate, we mean that your argument logically follows to bring us to that place. Basically that this expression here has all of the right constituents, not necessarily that you typed the right number into the calculator.
And finally, ensures by carrying through units or clearly applying the correct unit conversion at the end that the solution is given in the correct units. So this is kind of implicit in the solution that I've done here. Because I have worked with pronumerals almost all of the way through and then done my substitution at the end, the only unit that ever kind of makes an appearance is this kilonewtons that I stick on right at the end here. Kind of P turns into 30 kilonewtons. If you had substituted earlier into your equations, then I would have wanted to see strict carry through of those units throughout your expression. So either retaining the original units like millimeters or meters or newtons or pascals or whatever, and carrying those through at each step and then resolving them at the end, or resolving them at the start and getting everything into the same unit system, whether that's millimeters, kilonewtons, megapascals, or that's SI units, meters, pascals, newtons. Any would have been fine, as long as it's clear what you're doing and those units make an appearance at some point to tell us that you're either resolving them or you're kind of getting them into one unit system and then dropping them, as long as your argument is clear. Okay, cool. Nearly there. Let's take a look now at problem 5. So this was the talk-related problem, and because you had already demonstrated a lot of these competencies in the translating system or the linear system, we stuffed a lot of the criteria for this into a single problem. So what was previously broken up into several problems for the linear system is now just one problem for the rotating system. So the first was 1 mark associated with taking a method of sections cut, drawing a free body diagram, and showing that the internal reaction torque provides a right-hand rule-compliant polar or cylindrical coordinate system with your free body diagram, and then writes the equilibrium equation argument. So whereas those were previously separate questions, they're all in the same question now. And if I look at shaft AB, here are some of the indicators that one has done that correctly. For starters, they've taken a cut between A and B if they wanted to reveal the torque at shaft AB. So it could be anywhere along in between A and B. When they did that, they included all of the stuff to one side of the cut. So in my case, I included everything to the left of the cut. I have clearly that external torque TA indicated, and I have my internal reaction TAB exposed so that I can use it. When I say that a complete right-hand rule compliant coordinate system has been defined, I mean that this guy here has been defined. And so for polar coordinate systems, simply defining a theta would have been okay. If you defined theta as positive in one direction of rotation, that would have been fine. If you'd like kind of extra credit, except there's no actual credit given, if you would like vibes of good work, then defining z compliant with that theta is also satisfactory and good. And you do that using your right hand. You put your thumb in the direction of z, and your fingers should curl in the direction of theta. So a coordinate system needed to make an appearance defining positive theta. You could have defined TAB to be positive whichever direction you like. It would have come out to be negative if you got your assumption wrong. And when we say that you've made a good verbose equilibrium equation argument, we're hoping to see something like this. A sum of torques about z equals 0, preferably with a positive direction indicated, and then setting that or substituting or expanding that out into its constituent components and making an argument for why the internal torque should be something. So there were kind of marks associated with the coordinate system, there were marks associated with the free body diagram, and there were marks associated with the writing of the equilibrium equations. And then it's the same thing for shaft BC. You needed to take a cut between B and C, write that out, and finally expose that that internal torque was equal to whatever the value was for your particular quiz. Same deal. I've kind of defined my positive direction. I have a coordinate system. I've exposed that internal torque. And interestingly, in this case, it kind of contains all of the stuff that was in the part A problem as well. All right, moving on to the very, very last one and looking at the criteria. To do quite well here, what I need to do is define the maximum stress in each of the shafts as TR on J, substitute and rearrange for the unknown radius in each case. And all of the previous kind of expectations about good mathematical language apply here as well. So in my solution, I began by defining tau AB as TR and J and rearranging for the unknown that we actually care about, which is RAB, then the same for TBC. And that probably would have been sufficient to satisfy the initial requirement. Further, I've said that I'm going to set tau AB to 60 mega for the maximum allowable stress. And I've noted that TAB and TBC, the torques, have already been calculated in the previous question. Then I go and calculate J, which you were also expected to do. It was totally fine for you to just note that J for a solid shaft is pi on 2 radius to the 4. You didn't need to do the derivation. If you did, great, well done, but wasn't essential. And I've shown how that expands out for JAB and JBC. Finally, substituting those values in, being careful with your units. And so you'll note here, for instance, that I did have units to deal with. And so I've kept megapascals and Newton meters all the way through my working so that when eventually I do the substitution, I can resolve that. And if I was going to punch this into my calculator, I would punch in something like 1 on the cube root of 60 mega. So that's 60 E6 pascals, or 60 times 10 to the 6 pascals. Times pi on 2 on, that one was 400 Newton meters. And so I would like to work in SI units, and I would pump the numbers into the calculator like that. If you wanted to work in kilonewtons, millimeters, megapascals, you could put the numbers in appropriately, but you'll get the same result, just maybe a little bit trickier. And that's pretty much all she wrote. It was a relatively straightforward quiz, and I think the results reflect that. The class as a whole did pretty well. We promised you straightforward and scaffolded. We promised that we wouldn't be trying to trick you, and I hope that we lived up to that. I think you guys did great overall, and going into quiz 2 in the final exam, I'd really like to see you just focus on your mathematical language, focus on drawing really nice free body diagrams, taking really clear method of sections cut, and just spending a little bit more time writing out, enunciating whatever it is you're trying to communicate, because after all, that is the most important skill you're going to develop as an engineer. All right, great work, everybody, and good luck in quiz 2 and the final.